Oh, hi. Welcome again to our lecture. Today, I want to start chapter 3, chemical reactions and reactions stoichiometry. Just like the first two chapters, there are two parts for this chapter, part A and part B. Make sure you watch lecture recording for part B as well. As usual, I'll share my screen so that you see my illustration. If there are worked examples, you'll be able to follow on the whiteboard. Right now, you should be seeing the whiteboard PowerPoint slides. And I would like to start off by defining the terms you see, the title of chapter 3, chemical reactions and reactions stoichiometry. On the whiteboard, simply chemical reaction is a process by which reactants are converted into products, all right, into products. And chemists use chemical equations to represent chemical reaction. Um, Generic chemical equation A plus B, all right, A plus B maybe in gaseous state to form C plus D, maybe solid, maybe in liquid state. These represent chemical reaction. What we have on the left side of the reaction are these are the reactants, and on the right side of the reaction are these are the products. Later on, we will see how to interpret the chemical equations, what the addition means, what the arrow means, which I know you covered in introduction to chemistry. Here is the, before we look at the roadmap, chemical reaction. On the other side, quantitative relationship between reactants and products in a chemical reaction is simply stoichiometry. It's going from the Greek term, all right, stoichion, which means elements, and metron, which means measure, quantitative relationship between product and reactant. This is illustrated in Palan's chemical equation. For example, here, you look at the reaction between hydrogen gas to produce hydrogen gas and oxygen gas to produce a liquid H2O. The equation is not balanced. We're going to talk about balancing the equation by making sure that each atom on either side are the same. So what I want to do is balance the equation by placing coefficient in front of our reagent. Here we have one oxygen. We need to put that there. One, and there is one on this side of two hydrogens. No, we don't need 2 plus 2. So here I will need the 2. So here, 2, 4 hydrogens, 4 hydrogens, 2 oxygens, 2 oxygen. We say the equation is balanced. So if we have a certain amount of the reagent and we compare how much of the product will be produced, we are doing what we call, or looking using quantitative relationship, how much. Here is the roadmap for our chapter, all right? This is the outline. The first lecture will cover 3.1 chemical equation, 3.2 patterns for chemical reactivity. We'll see types of chemical reactions. We have about 7 of them. And then we look at the formula weight, whereby we relate what we can measure in the lab with the number of atoms. Remember, we cannot count atoms in the lab, but we can measure out substances. Section 3.4, Avogadro's number and the mole. We look at the Mole is a unit of measurement used by chemists to express certain number of things, which in this case, the Avogadro number here, you know, is 6.02 times 10 raised to 23. And we use this notation to represent Avogadro number Na. Avogadro, we look at in details in section 3.4, 3.5, which is part 2, empirical formulas from analysis, quantitative information from the balanced equation. This is where stoichiometry comes in. And lastly, we look at the limiting and excess reagent. Doesn't mean that in every chemical reaction, all the reagents are consumed or run out at the same time. Some reagents, there will be some leftover of a certain reactant we call excess reagent, and the one which is consumed completely or run out or limit the amount of the desired product is called the limiting reagent. All right. I've defined the stoichiometry earlier on in the previous slide. Stoichiometry is an area of study that examines the quantities of substances consumed and produced in a chemical reaction, right? Quantitative relationship between product and reagent is basically what? Stoichiometry. This was coined after the law of mass conservation. Remember, we talked about mass conservation previously by Antoine working with calcium carbonate and quantifying the amount of starting reagent and measuring the amount of the product, and turned out that the mass before and the mass after. And this is what he had to say, all right? I'm not going to read. This is in the text. You can look at it after performing several experiments, measuring out the reagent and measuring out the product out of the starting reagent. He concluded that matter cannot be created or destroyed, which is basically the law of mass conservation, and Antoine is credited for that law of mass conservation. We looked at that before. Now, let's look at the section 3.1 chemical equations. Chemical equation represent chemical reaction, okay? Chemical equation are way by which chemists present chemical reactions in or on paper, all right? I gave you earlier on that reaction between hydrogen gas with oxygen gas to produce liquid H2O, all right? 2, 1, and 2, we'll see later on that. This represent chemical reaction. This is balance. We cannot talk about balancing the equation in a moment. Balanced chemical equation, all right, which represent the reaction between hydrogen gas and oxygen gas in the formation of H2O. The arrow represent produce. This means here the reaction means produce. Give to give means to produce, to give, all right, to yield, all right. It can also mean to yield. A and B react with, all right. Addition means react with. This one means react with or combine with, and it represents the arrow separates the reactant from the product. You know how to interpret the chemical equation. Addition separates multiple starting or ending material. So we may have more than one reactant A plus B plus C to produce C plus D plus F. For example, it gives more than one what is produced and the starting compound. H2O product in this example, reactant hydrogen gas and what? Oxygen gas. Take note of what I pointed earlier on, that chemists use color coding to represent atoms of elements. Red sphere represent oxygen. This is the atomic molecule. We're gonna see the atomic molecule in a minute. Hydrogen gas is also the atomic for two hydrogen gases, molecules, reacting with one molecule of H2O to produce two molecules of H2O. All right, from the law of mass conservation, remember matter cannot be created or destroyed. Therefore, we need to balance out a chemical equation in order to obey the law of mass conservation. Using H2 again as to illustrate the concept or why we need to balance is, let's say we have hydrogen gas reacting with oxygen gas to produce liquid H2O. If you look at this equation, we have destroyed matter, breaking the law of mass conservation in the sense that we read this as two oxygens, but we have one oxygen on the product side. So we need to do what we call balancing the equation because of the law of mass conservation. And we balance the equation using the coefficient. A coefficient is a number which goes in front of a reactant or a product. We don't always, or you will not see one. If there is one, it's assumed that there is one there. We don't normally write one, even for subscript. You don't write one for one oxygen. It's just understood that there is one. So remember why we have to balance the equation. It's because of the law of mass conservation. Law of mass conservation. Below here is a combustion reaction between methane, CH4, with oxygen gas. To balance the equation, we put 2 in front of oxygen gas, all right? To balance the equation, we need to put 2 in front of H2 in any combustion reaction of hydrocarbon, CO2, and liquid H2 are produced. So here the point is you should be able to balance the equation. I know you cover this concept in Introduction to Chemistry. Please practice with end of chapter problems. All right. Practice with end of chapter problems, how to balance the equation. I'm just going to highlight there is no formula like one fit all equation you will use to balance any chemical equation. You have to practice. Just like maths, you don't read, but you have to practice until you get it. Let's see, why do we add coefficient instead of changing the, the subscript? If you change the subscript, you'll end up with a different substance. We don't want to end up with new compounds. Here is an example of changing a coefficient in the formation of H2O. Let's say you want to produce H2O from hydrogen gas and oxygen gas. If you change the subscript, let's say here we don't have this and we don't have this, and somebody change the subscript there to H2O2. We call this peroxide. It's no longer what? This is peroxide, hydrogen peroxide. All right. You'll end up with peroxide instead of H2O. So never change the subscript, only use the coefficient to balance the equation. Hydrogen, okay, you'll end up with hydrogen peroxide. This is hydrogen peroxide, which is an intended desired product if your objective is to make or produce H2O by reacting hydrogen gas and oxygen gas. So we need to do it. Use the coefficient in front of a reactant or a product in order to do it, to balance the equation. So this is unintended reaction, if you change the coefficient, never change the coefficient. We do not change the formula. Here is just illustration on how to interpret a chemical equation. Remember the subscript. If G is used, this means it is in gaseous state. If L is used, this means it is in liquid what? It is in liquid state. This means it's liquid state. We have S, which means this is solid state, all right? And AQ means aqueous means dissolved in water, okay? Dissolved, this means dissolved in H2O, all right? What has been used to dissolve? So if you see a subscript AQ means dissolved in H2O. This is just interpreting a chemical equation. If you have a symbol here, means heat is required, all right? So if there is something here, means you need to heat the reaction. You need to subject some heat energy for the reaction to proceed. If something is placed above the reaction arrow, this means a catalyst or platinum. In this case, platinum is the catalyst. Means speeding up the reaction, So there is an element here above the reaction arrow, means that is a catalyst. A catalyst is a species which does not participate in the formation of the product, but just only speed up the reaction. Now, the states these are the states. I was talking about states of matter for the reagent or product are often written in parentheses to the right of each formula, all right? I have here, this is in gaseous state, this is in gaseous state, this is in liquid state. Know what those subscripts stand for. All right, question in an exam could be when L is used, what does it mean? It means in liquid state. When AQ is used in a chemical reaction, it means dissolved in H2O. Water has been used to dissolve, or in other words, the solvent is H2O. The arrow above means, all right, if there is a symbol used to represent condition, in this case, over the reaction, delta over the reaction means heat is needed for the reaction to take place. This one means we need heat in order to do what? The reaction to proceed. I want to balance the equations, show you how to balance the equation from the example given there. So if we have a chemical equation, how do you balance? Take note of all right, take note of the physical states. So if I have here we have CO, that is carbon monoxide gas, plus oxygen gas to produce CO2. This is CO2 gas. You use trial and error. You can start with any element. All right, there is an arrow here. I just want to say carbon monoxide. So here, one carbon, you can use a check mark. This is balanced out. Oxygen here, we have, there is a 2 here, by the way. There is a 2 here, all right. So we read this, that we have 1 plus 2, 3 oxygens, we have 2 on this side. So we need to do what? We need to balance the equation. So if I put a 2 in front here, if I put a 2 in front of carbon monoxide, I'm just gonna use trial and error. I'm trying to charge my iPad. So here is, if I use 2 here, let's see. 2 carbons, and then I put 2 here. 2 carbons, 2 carbons. 2 oxygen plus 2, 4. We have 4 oxygen. So the equation is balanced the way we have 2 carbons, 2 carbons. 2 oxygen plus 2 oxygens make 4. 2 times 2 is 4. So the equation is balanced. Even though we don't see anything here, it's understood that there is 1. There is 1. Now let's see the second example. Al4C3. This is solid plus H2O. All right, going to AlOH3 subscript. This is solid plus CH4. Let's try if we say balanced aluminum. I'm gonna put 4 here so that I have 4 aluminums here. If you look at carbon, I have 3 here. If I put 3 in front there, that 3 means 3 carbons and 3 carbon on that side. Now, hydrogens, 2, I have 2 here, and these 4 multiply this 3 times 1 is 3 times 4 is 12, and then here I have 12 hydrogens. 12 plus 12 is 24. So here I need to do what? I need to multiply by 12 2 hydrogens to give me 24. So the way it is, I have 12 hydrogens times 2 is 24. I have 12 here plus 12 is 24. So hydrogens are balanced out. And here is what? Let's say oxygen 12. And then here is what? 3 oxygens times 4 is 12. So the equation is balanced the way it is. That's an example of balancing a chemical equation. It's trial and error. I know there are a good number of examples at the end of the chapter or in between the chapter and end of chapter problem also you should use to balance the equation. Let's look at C. C is an example on illustrate how you will be presented with worded chemical equation and you are expected to interpret the chemical names to formulas so that you can balance the equation. We learned earlier on how to write the correct formulas or what? Correct formulas for ionic compounds, correct formulas for molecular compounds. It's gonna haunt you if you don't know how to write the correct chemical formulas for compounds. How will you balance the equation if you don't know? So let's see, zinc, solid zinc. So zinc, you should know the chemicals symbol for zinc. It is in solid state, all right? React with what? Sulfuric acid. This is oxalic acid, and sulfuric acid is H2SO4. This is the formula for, and it is aqueous. All acids are aqueous. To produce zinc sulfate, zinc has a charge of positive, 2 sulfate polyatomic ion with an overall charge of -2. Crossover rule, they will cancel out. And this is aqueous plus hydrogen gas, H2, and this is gas. All right, hydrogen gas. So the question is, we need to balance out. Remember, hydrogen gas, oxygen gas, nitrogen gas. We looked at the diatomic atoms earlier on, and we know hydrogen. I don't want you to give me HS, hydrogen gas. You will see this for those who are taking the lab this semester, okay? Hydrogen gas in lab number 6, single replacement reaction when hydrogen is produced is hydrogen gas diatomic. No, so back to balancing the equation. We have one sink on the reactant side, one sink on the product side, so sink is balanced out. Let's see hydrogens. We have two hydrogens, all right, two hydrogens on that side. We can balance polyatomic ion as if it is a single unit. In other words, we have sulfate on this side, and we have single sulfate on what? On the reactant side. You balance as if it is a single unit, as if it is a single unit. So sulfate is balanced out, sulfate is balanced out, and we say the equation is balanced. So here we can just leave it the way it is. We say the equation is balanced out. Equation is balanced out. All right. There are several examples you can. There are several examples you can look at in the text. Any general chemistry. You can go on YouTube balancing the equation, all right? Practice until you are expert in balancing the equation. Let's move on to section 3.2, simple patterns of chemical reactions, simple patterns for balancing chemical reaction. And they are about 7, all right? There are about 7 types of chemical reaction. We need to learn the pattern so that we can predict the desired product from given chemical reaction, chemical equation. There is combination reaction, all right? Combination reaction is a reaction where 2 or more substances combine to form one. For example, A plus B to produce C. It's not only necessarily that 2, we can have 3A plus B plus C to produce D, so long as we have 2 or more combining to form one. Decomposition reaction, all right, one substance breaks down to produce 2 or more simpler substances. It's the opposite of decomposition. There is combustion reaction, that is a reaction between oxygen and substances. Combustion reaction, oxygen is involved. I want to add 4 or so more reaction. Here is the 4th one. You will see in experiment number 6, single replacement reaction. Single replacement reaction. There is a double, all right. It is of this type, this double replacement reaction. Reaction is acid phase neutralization, and then there is 7 redox reaction. I will post some additional resources to illustrate these types of reaction. You will see in the lab. It's not covered extensively in the text, but it is good to be well-rounded in types of chemical reaction, all types of chemical reaction. Let's start with the first one, combination reaction, a reaction in which 2 or more substances combine to form one. Here is just few specific carbon combining with oxygen to form carbon dioxide gas. In the formation of ammonia, nitrogen gas react with hydrogen gas to produce ammonia gas. And of course, balancing the equation, writing the correct formulas of the desired product. Please, if you look at all these, they form only one product. It's not plus, no, there is no additional product in combination reaction. The type of combination reaction you will see is a reaction between or combination between a metal and a non-metal. I've highlighted here metal and a non-metal because you need to use the periodic table to predict, all right, the ionic charge of a metal, an ionic charge for a non-metal. Unless you are dealing with polyatomic ion, you should be able to use the periodic table to predict. For example, simple reactions such as sodium solid plus, let's say chlorine gas is the atomic to form sodium chloride. In case you're wondering how did I end up with sodium chloride, understand that sodium is in group 1, chlorine is in group 2, metal and a non-metal. Cross over rule, this gives me the formula. And of course, we need to balance the equation. 2 chlorines. All right, we have 2 chlorines here. We have 1 here, so we need a 2 in front, and we need a 2 here, and there is a 1 there. We have balanced the equation. I will use another example here. Calcium solid plus, let's say, chlorine gas to produce calcium chloride. This turns out that you may think that chlorine was just fused into calcium, but behind the scene is using the crossover rule. Calcium group 2, chlorine 7, use that to form calcium chloride. And of course, it turns out that it's balanced out. Suppose we have, let's say, magnesium. This is a metal solid plus nitrogen gas. Look at how the equation will change. Nitrogen gas is the atomic to form. Use the periodic table. Magnesium is +1. Sodium is negative. Nitrogen is -3. So here, the crossover rule, that's the crossover rule. The correct formula for our product is Mg. 3 is coming from nitrogen and 2 is coming from magnesium. And then you have to go back and do it and balance the equation. There is a metal and a non-metal. Okay, so here we have what? 3 nitrogen. Let's just use trial and error. If I have 3 here to balance out that, there is 1. So the equation is balanced the way it is. 3 magnesium. All right. If you are dealing with metal or cation which form more than 1, let's say iron plus oxygen to produce iron. This is iron 3 oxide. Remember, this is iron 3 oxide. The 3 came from oxygen. So we need a 2 here to balance the oxygen. We need a 4 here. 4 ions. 2 times 2 is 4. And 2 times 3 is 6. We need a 3 in front of, oxygen gas, and the equation is plus the way it is. So basically, when you're dealing with cation which form more than one cation, you need to pay attention to the charges. So here, make sure you go back to the periodic table. All right. Now, magnesium. This is a good example to illustrate how you write the formula. Magnesium oxide is formed when magnesium ribbon is ignited in oxygen gas to form Mg. I know some of you may think that you end up with that. Crossing over, please simplify. Remember what we say about simplification. So if I have Mg, 2 from oxygen and 2 from magnesium, we can still simplify that. And the correct equation here is MgO. So if I have MgO, go back and balance the equation, that means we need a 2 in front of magnesium oxide. There is a 1 here, and then there is a 2 there. There is a 2 there for magnesium oxide. Magnesium oxide. So that's all what I want to bring to your attention in terms of combination reaction. In particular, the what? A metal plus a non-metal. Use the periodic table to predict the ionic charges. Be careful when dealing with ions which form more than one charge, such as copper 1, copper 2. There is chromium 3 or manganese 2, manganese 3, and so forth. Use the same crossover rule to write the correct formulas for the product, and then you balance the equation. As far as the decomposition reaction is concerned, all right, decomposition reaction, there are two types. One, decomposition of carbonates. All right, in the composition reaction, we can predict the pattern by which products are formed when carbonates decompose. All right, in the composition reaction, one product breaks down to form simpler substances. Here is an illustration of someone involved in a crash, and you see airbags. This is sodium acide. What that means, sodium acide is just decomposing real quick to produce nitrogen gas. It's given in the text to inflate the airbag. Here are a few examples of decomposition reaction, and all of them gives more than one product. This is what I wanted to point to you, how metal carbonate, when we say metal carbonate, it could be group 3, group 1 metal, group 2 metals. All right, how will you predict the product given? No, the key thing here is carbon dioxide and metal oxide. So the product here will be metal oxide plus CO2. So if I see CO2, you should be able to write the correct formula for metal oxide plus the CO2, and then you balance out the equation. What do we mean by metal oxide? Let's say calcium carbonate. Please make sure that you know how to write the correct formula for calcium carbonate. Calcium is in group 2, and then calcium is in group 2. And then carbonate is polyatomic ion with a -2. That's the correct formula for calcium carbonate. It's breaking down to give us calcium oxide. Remember, oxygen is group 6, -2. Calcium is in group 2. This is the correct formula for what? Correct formula for calcium oxide plus CO2. This is given over as a gas, and this is solid. The question is the equation balanced? Let's see. I have here one calcium, I have here one calcium, one carbon, three oxygen. So yeah, the equation is balanced the way it is. Say that the equation is balanced. It's based on the charge. Look at this charge on the metal. Suppose we have aluminum carbonate, for example. Let's see, AlCO3. There is a 2 from carbonate, and here there is a 3 from aluminum. This is solid. The composition reaction will give us aluminum oxide plus CO2, not CO3. I meant to say CO what? CO what? This is CO2. This is CO2 gas. Well, how many? This is metal oxide. All right. What you see here is metal oxide, and this is carbon dioxide. Carbon dioxide. Let's see, balancing the equation, two aluminum, so two aluminums there. Carbons 3 times 1 is 3 here. Let's say 3 here, so that carbons are balanced out. 3 carbons, 3 carbons. So I have here 3 times 1 carbon is 3. 3 times 1 carbon is 3. But now oxygens. 3 times 3 is 9. So here 3 times 2 is 6 plus 3 is 9. So coefficient here is 1, 1, and the equation is balanced. So balancing this equation is based on the charge on the what? The metal. It's based on the charge on the metal. So don't think that reading only on the PowerPoint slide and expect that you will see something similar to this. You have to practice extensively until you understand. Before we look at the metal or combustion, I want to just point out about hydrogen. Hydrogen carbonate. That means metal, hydrogen what? Hydrogen carbonate in this case. How will you predict the products and balance the equation? Metal hydrogen carbonate includes things as sodium, hydrogen. But before we look at that, what the products look like here is it will give you metal carbonate solid plus H2O plus CO2 plus CO2. Hydrogen carbonates produce metal hydrogen carbonate, liquid H2O, and CO2. Example is, let's say sodium hydrogen carbonate like that. If it is decomposing, this will give us sodium carbonate, that is metal carbonate solid, plus H2O, maybe gas, because it's plus CO2, and then of course you balance the equation by saying here we have 1 sodium, 2 sodium, so we need a 2 in front of sodium hydrogen carbonate. Sodiums are balanced out, sodiums are balanced out, sodiums are balanced out. 2 hydrogens, you see these 2 times 1 hydrogen, 2 hydrogens, we have 2 hydrogens. 2 times 1 carbon, so we have 2 carbons. 1 carbon plus the other carbon on that side gives us 2 on the product side. And lastly, let's see oxygens. 2 times 3 is 6. And here is 3 oxygens plus 1 is 4 plus 2 is 6. So the equation is balanced when you have 1, you have here 1, and you have here 1. You say the equation is balanced the way it is. That's just to give you how you predict hydrogen components, metal hydrogen carbonate. All right, I could have it as metal hydrogen carbonate like that. You should be able to predict the desired product in that case. So in terms of the composition, pay attention to hydrogen carbonates and carbonates. Carbonates produce the oxide of the metal and the CO2, two things. Hydrogen carbonate, metal hydrogen carbonate decompose to produce metal carbonate, H2 in gaseous state, and CO2 gas and CO2 gas. All right, let's shift gears to pattern number 3, which is combustion reaction. Combustion is simply rapid reaction between substance and CO2. All right, H2O to produce CO2. Combustion reaction involve oxygen. And there is a pattern here you can predict for hydrocarbons. You know, hydrocarbons are those substances which contain only what? Hydrogen and carbon. Hydrocarbon produce CO2 and H2O. So you can't go wrong with that. Two things produced from hydrocarbon. This is propane gas. In combustion reaction produce CO2 and liquid H2O. Produce CO2 and liquid H2O. So any hydrocarbon will produce those two products. Will produce those two products. I think this one we did the balancing equation before. All right, balancing the equation before, which is straightforward for you. All right. Before we look at that, let's see decomposition of decomposition reaction. Decomposition. Before we look at this, I want to look at the decomposition reaction of ethanol, CH. This is an hydrocarbon plus O2, and remember, this will produce H2O and liquid what? Liquid H2O. You can say liquid H2O or gaseous H2O. Doesn't really matter this gas. If you look at this one, it produces also in gaseous state. So this will be gas. We need to balance the equation, and if you look at the equation, 2 carbons on this side, all right. So we need a 2 in front of carbon dioxide, all right. 3 times 2 is 6 hydrogen on the product side. 5 plus 1 gives you 6 hydrogen. So we are done with hydrogens. Hydrogens are balanced out. Now, for oxygen, 1 plus 2 is 3. 1 plus 2 is 3. Here we have 3 plus 4 is 7. 3 plus 4 is 7. So what we need to do is to make this 7. We have 3 plus 7, we will have here 7, 3.5. 7 over 2 is 3.5. So you have 7 divided by 2 is 3.5. So you don't need a fraction here. So what we need to do is multiply by 2, by 2, by 2, by 2, so that this will change to 2. We will see that, change that to 2. This will change to 7, and this will change to 6, and this will change to 6. Let's say this is 7, this is 6. Let's see how many couples we have here. This is 2 times 2 times 2 is 4, and here we have 2 here. So let's say we have 2 couples. So here is no 4 here. This is what I meant to say, 4. So here 2 times 2 is 4. 4 times 1 is 4. So couples are taken care of. Let's see hydrogens. 10 plus 2 is 12. Look at the hydrogen. 6 times 2 is 12. So hydrogen is taken care of. Now, oxygens are 2 plus 14. That is, you see, this is 7 times 2 is 14, plus 2 is 16, so this is 6. 4 times 2, that will give you 8, 14. So we have that, it will give us 14. So here we have here 6. You see here 6 plus 8 is 14. Here, if we need to make this is 12, we need to have here 6. So here is 2, 5. So 10 plus 2, no, 6 here. So that's 6. 12 plus 2 is 14. 6 plus 8 is 12. The equation is balanced from the combustion reaction of ethanol. This is combustion. I'm just covering here where CO2 and H2O are produced. So remember, in combustion reaction, CO2 and H2O are produced. This was just going back to the balancing equation concept, which we covered earlier on. And if you look at the first one is already balanced. A is already balanced. This will give you lead to, this is lead 2 carbonate. Lead 2 carbonate decomposite lead oxide, all right? Lead 2 oxide solid, this is solid plus CO2. This is the composition of carbonate, by the way. The composition of carbonate. This is here, the combo. And then B is combustion. This is combustion reaction, which is simply the team C4 plus O2 to produce CO2 plus H2. We need to balance this liquid H2 here to balance the combustion reaction. So here is we have two carbons on the product side. We need to put in two here. Let's say two there, just to balance the carbons. Carbons taken care of. Hydrogen's 4, so we need a 2 in front of H2 to balance the hydrogens. Hydrogen's 4, hydrogen's 4 on the product side. On the reactant side, we have 2 oxygens, and on the product side, we have 4 plus 2 is 6, so we need to multiply by 3. Yeah, this is an example of combustion reaction. And though you don't see anything, that's assumed to be 1. And lastly, C, that is combination reaction. This is combination what? Reaction. Combination reaction. Which Al, all right, solid plus Cl2, chlorine gas to produce aluminum chloride. Balance this equation. On the product side, we have 3 chlorines. On the reactant side, we have 2. So if we use trial and error and put 3 there and put 2 there and say chlorines are balanced, we have 6 on the product side, we have 6 on the reactant side, but the number of aluminums on the reactant side has changed and we need to put there. So those are the coefficient of the balance equation for combination reaction. So these 3 examples here illustrate the 3 types or 3 patterns of reaction decomposition, combustion reaction, and in particular decomposition of carbonates and combination between a metal and a non-metal. Please use the crossover rule. Predict the ionic charges from the periodic table in order to write the correct formula before you balance the equation. Let's shift gears to section, all right, 3.2 and formula weight. We want now to relate the atoms, all right, with the something we can measure in the lab. And basically, the formula weight is the sum of atomic weights of atoms in a compound. You should be able to interpret the numbers on the periodic table, such as element carbon, there is a number above it and there is a number below it. This is atomic weight. Atomic what? Atomic weight, whereas this one is atomic what? Atomic number. How do you determine the atomic weight or rather formula weight? From the word formula weight, it gives the formula. Sodium chloride is the formula. What is the formula weight? Formula weight is simply the sum. So you have to look at the periodic table, look for the atomic weight 9898, and chlorine is 35.453. When you add these two numbers, I'm getting those numbers from the periodic table. It might be slightly different depending on the periodic table. 22.9898 plus 35.453. So this is what? This is 58.442. All right, 8.4428. This is grams, not grams. We cannot talk about grams. Since we are talking about the formula, we will see later on the this one, AMU, atomic mass unit, why we use that. This is how you calculate the formula weight. The numbers you see here is of the periodic table. You will be given that in the exam. I'll give you the periodic table and you should be able to interpret using the numbers for each chemical symbol on the periodic table. It has some significance. For example, here sodium is around 23 using one place of decimal. And by the way, this text we are using uses only one place of decimal in calculation throughout the text. So you may see some illustration. My worked example having 2 or more places of decimal, but in the text, one place of decimal is used. This AMU is atomic mass unit, which scientists use. I think I mentioned earlier on that 1 AMU, if you want to relate what you know, is 1.6, 6 times 10 raised to negative 24 grams. It's a small number, so chemists use this AMU. For ionic compound, we use empirical formula. So if you are to find the formula weight for sulfuric acid, you're gonna look at the hydrogen times 2 from the periodic table. So if you have on the periodic table, you see this, all right? Inside box for hydrogen, there is either 1, and then number 1, this is the atomic weight. Which you will have to do what? You'll have to multiply by 2 and for sulfuric, for sulfur and for oxygen. So here 2 times atomic weight of hydrogen plus 1 times atomic weight of sulfur plus 4 times atomic weight of oxygen, and you end up with 98.1 AMU atomic mass unit. That is for what? We talk about the formula weight, but for molecules are those compounds which consist only of what? Consist only of non-metals. We talk about molecular weight, e.g. Hydrogen or rather H2O, this is a molecular weight. We talk about MW for molecular weight. So if I am to do this will be 2 times for hydrogen, 2 times 1.01, it's gonna give you 2.02, and then oxygen is 1 times 16, just to round off that, it's gonna be 16.02, and for H2O, we talk about this is 0, 2 AMU, atomic mass unit. We talk about the molecular weight if we are referring to molecules. The simplest form of molecular compound. Molecular compounds are those made up of what? Only non-metals. So when you look at glucose, for example, this consists of carbon, hydrogen, and oxygen. They are non-metals. So that's how you find each atomic mass unit AMU. The numbers you see here just from what? From the periodic table, Let's see example on how to find the molecular weight of a few compounds here on the learning check, the PowerPoint slide. What I want to point here is at this point, you should be able to translate chemical names to chemical formula so that you can use the periodic table to proceed with the calculation, especially the first two. So if I look at the first one, A, chromium, you should be able to see, to write down the correct formula, chromium, and then sulfate is polyatomic ion with an overall charge of -2. So correct formula is Cr. 2 is coming from what? 2 is coming from sulfate, and then use parentheses and sulfate right there. This is a challenge in itself. Translating chemical formulas, no, chemical names to formulas. If you don't know how to write, somebody might write even CRS and say that is chromium sulfate. All right, or even CR3 like that, chromium 3, and something I don't even understand. All right, please follow the guidelines, write the correct formula for compounds so that you'll end up with the correct formula. So this is what we need to find the formula for that. And what you do is chromium, all right, you say chromium is 3 times from the periodic table, 51.9961. We have 3 of them. And then sulfate, we have no, chromium, we have 2. We have 2 here. Sulfate, we have 3 times 32.065. This is of the periodic table. And then oxygens, we have 12 because of 4. You see here, 4 times 3 is 12. So I'm gonna say 12 times 16.00. It's gonna give you that. This is 103.99. If I'm not wrong, please take that. And this is 96.195, and this is 192. When you add up everything, this will give you 392.3 AMU. That's how to find the molar mass. Please use the periodic table, write the correct formulas of compounds, and you will not go wrong. So for molecular compound, phosphorus, tri, that means tri is 3 chlorines, all right? Phosphorus here is 30.1, no, 30.9738, and chlorine, so earlier on, this is 3, this is chlorine times 4, no, 35, this is chlorine is 35, 24, 5, 3. AMU, this is AMU. So if you add everything, this should give you 137.3 AMU. Check that, all right? This is an example of worded chemical equation. Chemical formula translate to correct formula. This is the word, that chemical name translate to chemical formula. Use the periodic table and determine the formula weight or molecular weight. The last one is pretty straightforward. Please try on your own. This should give you 158.0 atomic mass unit. This is for potassium permanganate, MnO4. Please try on your own. You should be able to get this atomic mass unit for the last one. Atomic mass unit for the last one. So, all right. Now, please go back again, practice more, especially on the worded chemical names. End of chapter problem. The odd numbered ones, you'll have the answers at the back of the book. Let's look at the percent composition. Forensic scientists sometimes, chemistry, want to determine what a known substance is, and sometimes they use percent composition to determine, all right, its composition by mass, and then compare to what we know. And simply, this is the equation for percent composition of an element in a compound. Means you have to find the number of atoms in the compound multiplied by the number of atoms, all right, multiplied by its atomic mass. Number of atoms, not number of atoms. This should be atomic mass divided by the formula weight of the compound times 100. So please remember to change this to atomic mass. Maybe you'll see when we see the percent composition of glucose. This is the atomic or the molecular weight of glucose. All right, percent composition by carbon is 6 carbons. By the way, 6 C H. All right. For that, the hydrocarbon for carbon, see this is H2. Six. So if we are looking for percent composition by carbon, you just have to multiply the atomic mass of carbon times 6 of them, because that's where that is coming from. 72 of 100, and we have 40%. 40%. If it is hydrogen, we're gonna have that. Just to make sure that we know how to find the mass percent. You know how to find the molar mass, you will get that. Please solve more on percent composition. Before we look at our section 3.4, which is the last part for part A of the lecture, let's see, calculate here, example on percent composition, calculate the percent, all right, percent composition of potassium in potassium pi mass. This is pi mass. I wanted to say pi mass in K2 PTCl. This is called potassium. Hexachloroplatinate, all right, hexachloroplatinate. We want to know the percent pi mass in this compound. You should know the molar mass of, or find the molar mass of potassium hexachloroplatinate using the periodic table. And this one I already determined the molar mass is 485.99 grams per mole. This is the molar mass, or not, that. This is AMU. I wanted to say atomic mass unit. Atomic mass unit. So if we want to know pi mass percent composition of potassium pi mass in that compound, we'll say that percent potassium is 2 times 939.098. We have two of them over 485.99 times 100%. 100% give you 16.1%. This is an example on how to find the percent composition. Percent composition. So if it was chlorine, we will multiply by 2. If it is platinum, we just have to put the atomic mass of platinum at the top, and then atomic or the formula weight of the compound below, and then we multiply by 100. If we have 3, we multiply by 3. It's pretty straightforward. Pretty straightforward. Let's move on to 3.4, Avogadro. Avogadro number is simply a number in honor of Amadeo Avogadro, who he was working with different gases and established that there was equal number of atoms of different gases in what we call 1 mole, all right? We'll define that 6.0 2 times 10 raised to 23 things. In other words, anything which has this numerical value, we call this Avogadro number. We call that Avogadro number. So we call that Avogadro number, and it represents the number of things. Chemists use this number to state the number of things in one mole. Usually it's hard to count the number of molecules, but we can relate to masses using what we call one mole. You know, a dozen of eggs has 12 eggs. One mole of anything has Avogadro number. And this represents the number of atoms in exactly 12 grams of isotope of carbon-12, all right? Isotope of carbon-12. This is the only isotope which is reproducible, okay? The rest varies, so they use this as a reference. Well, the number you see, it's not 60, but 6.0, sorry about that. It should be 6.0 times 10 to positive 23. We call this Avogadro number. Where we are going with this is we will be using as a conversion factor. Now, in the previous section, I talked about the atomic mass unit, that when we have only one, but when you have Avogadro number of things, we change to same numerical value, but the unit is grams per mole. For example, 1 NaCl, this will weigh 58.44 atomic mass unit, but 6.02 times 10 raised to 23 Na atoms will weigh 58.44 grams. That is why you see molar mass or formula weight is given as 58.44 grams per mole, because we are talking about the Avogadro number. Differentiate between the units here, that when you have a single unit, if I can take only one sodium and one chlorine put together, this will be the mass in AMU, that is 1 unit. But Avogadro number will weigh the same numerical value, but the unit will change to grams. Therefore, we say grams per mole, 1 mole. So in other words, 1 mole of NaCl will weigh 58.44 grams of NaCl. This is just the same as that, grams per mole. Can have that. So here is illustration on how the formula weight relates to molar mass, and all they have the same number of molecules or atoms, which represent 1 mole. Well, for an element, all right, let's say here, I'm just going to draw here 3 things you should pay attention to. Element on the periodic table, element on the periodic table. 1 mole equals 6.02 times 10 raised to 23 equals to what? Atomic mass. You just have to equate to what you have on the periodic table. But for the formula unit, all right, formula unit, 1 mole equals 6.02 times 10 raised to 23 equals to the formula mass or formula weight. It's the same thing. Use the periodic table. Here in this one, use what? Use periodic table. Use periodic table. Gonna have that to use the periodic table. Now, for molecular compounds, 1 mole of molecules for 0.2 times 10 raised to 23, all right, 23, which is equals to molecular weight, all right. So that is what, here is the molecular weight. You're gonna have that as an equivalent statement. Again, this is from what? From the periodic table. Use the periodic table to find the molar mass. The difference here is this is any element on the periodic table. This is for ionic compound. I should have said ionic, maybe ionic compound. So here, where we are going with this is converting between the mass in grams to atoms or molecules or particles, and then the moles. We will be doing dimensional analysis from here, all right? Make sure you understand the difference between molecular compounds and ionic compounds. It's the same thing. Therefore, the number of atoms of element in 1 mole is the subscript in a formula. The number of atoms of an element in a mole is the subscript. We're gonna see that in an example. Here is a roadmap in converting between either grams and moles. If you look at here, this is the grams, formula mass, molar mass. So if you want to change to moles, use the molar mass to change to grams and moles. To change from moles to formula unit or formula units to moles, you use Avogadro number. From here, this is the periodic table. Avogadro number is 6.02 times 10 raised to 23 as your conversion factor. You should be able to change that, all right, based on what you are given. Moles provide a bridge between molecular scale to the real world. So in other words, there is no way we can count the number of moles, but we can measure out the mass of substances in the lab. Here is an example. How many atoms are in 3 grams of copper? Well, from the periodic table, 1 mole, right? From the periodic table, remember I said 1 mole of copper equals 6.02 times 10 raised to 23 atoms of copper, which is equals to 65.63 grams of copper. So we will use 63.5, not 60. This is the molar mass, 65, 3.5 grams of copper. What you see here, 1 mole equals to. So we will use Avogadro number as our conversion factor. So if I'm given here 3 grams of copper times, we are looking for what? Look at these atoms. So if I'm looking for atoms, will be at the top, atoms of copper. I want to get rid of grams of copper. So this and this will be my values used to generate conversion factor 0.2 times 10 raised to 23 and 63.5 grams. So that grams and grams will cancel. Please make sure you cancel or you reconcile the units. You reconcile the units. I'll go with this setup so long as you know what you're looking for. Start with the units, make sure that you cancel out. The challenge you may face if you don't practice is handling the exponential on your calculator. What I'll do is practice this one significant figure times 10 raised to 22. Make sure that that's the value. This is atoms right here. So I'm gonna use my calculator to confirm. So this is 3, all right, 3 times 6.2, 02 raised to 23 and divided by 63.5. Yes, it is to 1 significant. That is 3.2 because it was 1 significant here. I see I have 2.8 times 10 raised to 22. But because this is 1 significant, we'll round off to the 1 significant, and that's what you should put in or key in your calculator. Let's see. Learning check here. Calculate the following quantities: mass in grams of sucrose. All right, mass in grams of sucrose. You need to find out the mass in terms of 0.1. At the outset, from the definition, you should know that 1 mole of sucrose, which is C12H22O11, contain Avogadro number of molecules, 23 molecules, which is equals to what? It weighs, all right, 342, all right, 342.3 grams of C12H22O11. That is the definition of 1 mole, a statement which you should know. But if you look at here, mass in terms of this, so we will look at the moles and grams right here. That is what we will use to generate our conversion factor by saying 0.105 grams. We're looking for, this is moles, not grams. So here's moles. I have this 1 mole of C12H22O 11. All right. So here is 342.3 grams of C12H22O11. 11. All right. So unit cancellation, moles and moles, and this should be 35.9 grams of C12H22O11. Look at how I generate, or what I generated from what? From the equivalent statement here. I'm relating moles, which you should know by definition, with the molar mass. How did I end up with this? You need to use the periodic table. You can Google out if you're doing the homework, but remember to learn how to use the periodic table to find the molar mass. This is the molar mass of sucrose. Set up your equation. Look at what you are looking for, and then you do the unit cancellation. 3 significant figures, 3 significant figures. All right, that is part, that is A, and then B here. What is the mass in grams of 2.50 times 10 to negative 3 moles of ammonium phosphate? Before you determine the molar mass of ammonium phosphate, you should be able to write the correct formula. Look at this. Ammonium polyatomic cation and phosphate polyatomic ion. Therefore, ammonium phosphate is NH4 with a subscript 3 here. Well, we don't have the subscript for phosphate. That is the formula we need to use. And if you check using the periodic table, the molar mass, all right, molar mass for this is 149.1 grams per mole. 149 grams per mole. So in other words, once you know that, you should understand that 1 mole of NH43PO4 equals to Avogadro number equals to 149.1 grams. This one, we are determining the grams and from the number of moles. So the only numbers we need is what I have in the box, required relating atoms. You see this? Molecules. I should say molecules. It's the same thing. And the grams. So I'll write down just the way we did what you are given, 2.5 or 0 grams of NH4, grams of NH4, three PO4. All right, times. We want to get rid of grams, so 149.1 grams of NH4 and here is the Avogadro number times 10 raised to 23 NH4 PO4. So that this and that will go. All right. No, we're looking for what? Moles, not grams. Sorry about that. Yeah, so this is what I need to change. We need to change a little bit here. That is a wrong setup. So what I need to do is change these to moles. We are looking for times 10 raised to, this is times 10 raised to negative 3 moles times 6.02 times 10 raised to 23 molecules. And here is 149.1 grams of what? We want to find the mass, NH for PO3. So that moles and molecule will go away. All right. And this should be 6.19 times 10 raised to 20, negative 25 grams of NH for parentheses is 3PO4 ammonium phosphate. The challenge is if you don't know how to key in the Avogadro number or handle the exponent on your calculator, you may not get the right answer. You may not get the right answer. That marks the end of part A. I'll come back again for part B of this lecture. In the meantime, make sure you practice end of chapter problems. The odd numbered one have answers at the back of the text that should help you for more practice. Thank you.